that moreover, thinking that your personal data are insignificant or that you have nothing to hide, a big mistake. Honestly, who hasn't ever tried to use a private browser just to ensure that your searches, online activities are not stored in your browsing history? Either because they are too intimate, you don't want others to see what you are looking for, or just because you don't want your cookies to reveal your browsing history to certain websites like flight and ticket comparator websites. Besides, a well-known saying states that if a service is free, then we are the product, which means that our personal data can be a gold mine for others. And if they fell into wrong hands, they might be used against us for extortion, non-transparent purposes, or even behavioral manipulation. So please remember that the right to privacy is a fundamental right. It's not a privilege, and we all should have the freedom to selectively disclose what we want to who we want. And with the rise of cloud computing, it makes it even more complicated to safeguard and protect our data privacy. Many of us rely on cloud services. Therefore, protecting our privacy has become a major concern for many people. At Zama, we believe that this matter doesn't rely on internet users, but rather on developers and cloud providers. This is their duty to protect and safeguard the data they process.
I think you're touching the screen with your hair and lips.
So regarding my background, I've been working for Zama for almost a year now as a machine learning researcher. Prior to that, I worked in a consulting company as a data scientist, mainly on data quality and data governance projects. And before that, I did my internship at Thales. I studied machine learning at University. So now at Zama, I contribute to the development and the enhancement of the machine learning library, Concrete ML library. All our work is open source. And the solution we provide to safeguard data privacy is based on a technology called TFHE that I will show you in the next slides. Regarding the agenda, I'm planning to explain what's FHE and TFHE. Of course, I saw that in the audience, most of you are from cryptography background, so it will be explained from a data scientist point of view. And then I will get to the juicy part where I will explain how to convert a machine learning model to its TFHE equivalent, and I will show you a demo with some experiments. Okay, so let's start with the main technology, which is FHE. FHE stands for fully homomorphic encryption and is a family of schemes. So, like all encryption schemes, it allows you to encrypt and decrypt messages. By the way, on Monday, you had a presentation about CKKS. So, CKKS is also another specific scheme of FHE, and TFHE is another specific scheme of homomorphic encryption. And I will talk about it later. So as I told you, it allows you to encrypt and decrypt messages. It also allows you to perform computations on encrypted data without ever decrypting them. So in this example, X is a plain text data, which needs non-encrypted. The encryption is represented by this blue box with the log, and the whole content is called a ciphertext, which means encrypted data. With fully homomorphic encryption, you can add homomorphically to ciphertext or multiply homomorphically to ciphertext. In the same way, you can multiply a ciphertext by a scalar, and the result is another ciphertext. So here I represented the. So here I represented the homomorphic operation in a different color because in the ciphertext space they are more complicated and different than the plain text space. An important thing to know, and it was also highlighted by the other speaker, is that when you create a ciphertext, a certain amount of noise is added for security reasons, so you cannot get rid of it. So here, this noise is represented by the mirror, and at the beginning, the noise is very small. But as soon as you start performing consecutive operations on your ciphertext, the noise will start to grow. And more especially for the multiplication, where it grows faster than the addition. And this noise becomes problematic when it exceeds a certain threshold, here represented by a red line, because it compromises the original message and the decryption is no longer possible. Fortunately, in cryptography, we have a complex crypto algorithm called bootstrapping that overcomes this noise issue. I won't explain this algorithm since I'm not an expert in cryptography, but the idea behind the bootstrapping algorithm is that it achieves noise reduction thanks to a specific key called the bootstrapping. This key is public, so it doesn't compromise the security of the scheme. And by using this key, you will reduce you will get another ciphertext here with less noise. And that will allow you to perform other computations. So in practice, by chaining homomorphic operations and bootstrapping, you are able to evaluate any size of operation graph. Now, let's see why TFHE is so appealing and when it can be used in real-life use cases. If we take the example or the scenario of cloud computing, let's say that you have that you would like to apply a funny Marvel comics filter on your image. So currently, you sent your image to the cloud. It will be encrypted thanks to the HTTPS protocol. But once it arrives in the cloud, it gets decrypted for computation reasons. And once the computation is completed, the data is re-encrypted and sent back to the user. Now, if we take the previous example, but this time using fully homomorphic encryption, in this setup, you will have to generate two keys. You will have first what we call an encryption and decryption key and an evaluation key. The encryption and decryption key will allow you to encrypt and decrypt your image locally, and it's private, so you are the only owner of this key. You have Regarding the evaluation key, it's a public key, so it doesn't compromise the security of the scheme, of the scheme, and it will allow other parties to perform computation on your encrypted data. So locally, you will generate these keys, you will encrypt your image, and you will send it along with the evaluation key to the server. And it remains encrypted in the server, even for the computation phase. So thanks to this evaluation key, the server will be able to perform computations on your encrypted data, just like it used to do on non-encrypted data. And at the end, the result is sent back to the user. And of course, since the user is the only owner of this encryption and decryption key, he will be able to retrieve the information. And in this scenario, the whole process is encrypted. So TFHE adds a new layer of encryption. The location of the server and the state's privacy regulation are irrelevant since your data are encrypted. And the cloud learns nothing about your data because they are encrypted. Okay, so let's showcase the previous example in a real demo. So far, in the machine learning team at Zama, we published 3 use cases. The latest one, healthcare prediction on encrypted data. We have the image filtering that I will show you, and sentiment analysis on encrypted data. I invite you to try them out, and they are available in the Hugging Face space. Okay. So here we are simulating the behavior between a client and an unknown and untrusted server. So let's say that you have on your personal device some personal data. We choose, for example, this one. Let's say that the cloud offers a set of filters. Take, for example, the black and white. So first you generate the keys, evaluation and private key. You encrypt your data locally. You send the encrypted image to the server. The server executes its operations on your encrypted data using the evaluation key, of course. You get back the results. And as you can see, it's you can see all the nodes because it's encrypted. And locally, you decrypt the data and you get your image with the new filter. Of course, you can apply fully homomorphic, other use cases in fully homomorphic. For example, the healthcare use case. We all know that processing medical data is a big challenge in machine learning because the patient data are really sensitive. We also think about the face recognition or the speech recognition use cases, and even more use cases. The thing that I didn't say is that bootstrapping is a costly operation in fully homomorphic encryption. And at Zama, we use a specific scheme of TFHE. Like CKKS is another specific scheme of TFHE. So TFHE stands for Torus Fully Homomorphic Encryption. Torus basically means real numbers modulo 1, which means numbers between 0 and 1. And with this scheme, with this encryption scheme, you will have all the properties of the fully homomorphic encryption, but with some improvements. For example, the bootstrapping becomes a programmable bootstrapping. Programmable here means noise reduction and evaluating any univariate and nonlinear function using a mechanism called table lookup. So as I said, table lookup is the mechanism that will allow you to evaluate nonlinear functions. So basically, it's a table. It's a table that for a given set of integers, given possible set of integers, maps them to another possible set of integers. This table introduces nonlinearity, which is really interesting for the machine learning use case. And programmable bootstrapping and table lookups are not handled in the concrete ML library, but in a lower stack called concrete Python. So as a data scientist, when you use this library, you don't have to implement them by yourself. But just to give you an idea of how the implementation of a table lookup would look like, I added an example from concrete Python to give you an idea of how this example might be implemented with table lookups. And since the programmable bootstrapping manipulates ciphertexts that comes with ciphertexts that come with a certain amount of noise, it means that when you use this table lookup, you will have an error probability. This error probability is manageable, even in a concrete ML library, and it's called the pair, which is defined as the error probability of a single table lookup of being incorrect. So in our example, let's say that the correct value is the index -1, which, the index is 1, which refers to the value -1, and the error probability may shift this index either to the right or to the left. And so we get the new value. Okay. So, so far I briefly explained how the technology works, why it's so appealing, and when we can use TFHE. But for the data scientists in the audience, rest assured you don't have to understand and master all the crypto concepts to use concrete ML library, since the table lookup and the programmable bootstrapping are handled under the hood. So just be a data scientist to use concrete ML. Now, how to apply TFHE on machine learning. And from now on, if I use TFHE instead of TFHE, it's a shortcut mistake. So in machine learning, to build models in machine learning, you need two main operations. You need a matrix multiplication, which includes additions and multiplications, and nonlinearities for nonlinear and the nonlinearities for activation functions like value, sigmoid, and so on, and also test comparisons for trees. On the TFHE side, we have those equivalents. We have the homomorphic operations that I mentioned earlier, which include addition and multiplication, and either the multiplication by scalar. And we have the table lookup that will allow us to evaluate the nonlinearity. And for the moment, in the machine learning team, we are only focused on the inference phase, which means that only the input data are encrypted. So the weights and the activations of your model are unclear. They're not encrypted for the moment. And so the training, you have the flexibility to train your model as you wish. Regarding concrete ML library for built-in models, we use the fit of scikit-learn. And regarding the training in fully homomorphic encryption, it's a work in progress, and it will be available in the concrete ML pipeline in the upcoming quarters. Like all technologies, TFHE has its constraints. From the machine learning point of view, TFHE has two main limitations. First, it operates only over integers. In machine learning, we can overcome this limitation by using the quantization, which means that before performing any operation in TFHE, you have to quantize your input. And we saw that the table lookup takes as input integers. The second limitation is the time. Because performing operations over encrypted data are slower than on plain text data. So to get fast and reasonable execution timing, you need lower bit-width precision. Regarding the quantization is the process of converting continuous data to discrete numbers within a fixed range, and in our case, as few bits as possible, and all the inputs and intermediate values has to be converted to integers. And for the quantization, if you would like to quantize a floating point value, it's really easy. You just have to determine the quantization parameters and which type of quantization you would like to apply, if it's an asymmetric quantization or a symmetric quantization. So in this example, I illustrated the asymmetric quantization. The quantization parameters are the 0 point, the scale, and the bit-width precision. So the scale is a floating point value that represents the step size of your quantizer. The 0 point is an integer value that represents the quantization of the real zero. It's really important in machine learning because we don't want to add additional errors in our computations for operations like quantization of the value or the 0 point. And usually in machine learning, you will perform your computations on floating points data using 32 bits or 16 bits. And with the quantization, you can perform these operations using integers that are represented with smaller number of bits, resulting smaller accumulators. So in this picture, we can see the impact on the quantization. So for the image on the left side, for each channel, each pixel is represented with 8 bits, which means 256 values. And the more you go to the right, and the less precision you will have. And as we can see, with an image represented with 1 bit, the image looks pretty unclear because we have a loss of information. And in the literature, we have 2 famous weight quantization algorithms. We have the post-training quantization and the quantization-aware training. For the post-training quantization, it's a really straightforward technique where you take a pre-trained model, you take the weights and the activations of your pre-trained model, and you convert them to the lower desired precision. But to do that, and without necessitating any retraining, so straightforward technique. But to do that, you need what we call a calibration data set. And this calibration data set is usually a subset of your training set, and it has to be a representative data set. This method, a representative data set that will allow you to determine the quantization parameter that you will use to quantize your inputs, weights, and the activations. So it's a simple technique, but it's also subject to quantization error. Regarding the quantization-aware training, unlike the post-training quantization, it requires what we call a fine-tuning phase or a training phase to adjust the quantization parameters. The advantage of the quantization-aware training is that you have less quantization errors, and that's why it's widely used for neural networks. Now let's see the impact of the precision on TFHE. So in this plot, we have the accuracy for different quantization bits for a concrete XGBoost model. So in our jargon, we put concrete in front of machine learning models to specify that they are FHE friendly. So as we can see, the more we quantize, and the smaller the size of the accumulators, but also the less precise the precision becomes. Regarding the inference timing, the more you quantize, and the faster the inference time becomes. So as a data scientist, when you use TFHE with concrete ML library, your big challenge is to find the right balance between maintaining a good accuracy and a reasonable trade-off. A reasonable latency. Okay, before going to the Compute ML library, do you have any questions? Yes?
Maybe a quick question about the quantization in general. The 0 point value, is it better to pick a smaller integer value or a larger integer value?
So you have to compute this 0 point. So there is another formula to compute the 0 point, and it will depend if it's an asymmetric or a uniform quantization or a symmetric quantization. But you have a formula.
I have a question. What part in the process is the evaluation key used?
Part of the process is
not
the quantization.
No, you said that for this encryption, for the fully homomorphic encryption, we need the encryption decryption keys, which are asymmetric, and then we also need an evaluation.
It's one key.
Symmetric symmetry?
I'm not sure, whatever, for encrypting, decrypting, and then aside from those, we need some kind of evaluation key.
Yeah.
So where does the evaluation key stand in this process? What is it used for?
So in TFHE, I said that you need to create two keys. You have your encryption and decryption key. Okay, this is one key, and it's private, and you have an evaluation key. This evaluation key is generated from your private encryption and decryption key, and based on the circuit. So, and this key will allow other parties to perform computations on your encrypted data.
Okay, so it's derived from the private key and you need it for the computation.
Yeah,
okay.
And it's a public one, so you can share it with
Okay, thank you.
It's a bootstrapping case, actually.
Okay.
It's the simplest way.
Oh yeah, it's for the bootstrap.
Yeah, it's really good for bootstrapping.
Okay, regarding complement library. So we tried so we did our best to make ConcreteML library as similar as possible to scikit-learn library, which is a really well-known library in computer science, for data scientists, I mean. And it's compatible with Torch, ONNX, and Keras. For those who have tried scikit-learn library, could you raise your hand just to see how many? Yeah, okay. Not that much, but. Okay, so in ConcreteML library, we distinguish two main categories of models. We have what we call the built-in models and the custom models. Regarding the built-in models, they include linear models like linear regression, logistic regression, and linear SVM, and so on. You have the tree-based models like decision trees, random forest, and XGBoost. And neural networks for the multi-layer perception for regression and classification. And regarding these built-in models, they are used just like the models of scikit-learn. So you don't have to implement them or worry about the quantization process. Or how to convert them to their TFHE equivalent. So everything is automated for this built-in model. The new hyperparameter is the quantization parameter that you will take care of. Regarding the custom models, they are usually built using PyTorch or Keras library. So since you have custom layers, it means that the developer has to do some additional work to convert them to their TFHE equivalent. Now we will see how to convert machine learning models to their TFHE equivalent. Okay. So all the models that I mentioned before have something in common. They can all be represented as a computational graph, which means a succession of matrix multiplications, addition, and non-linear operations. So as soon as a model can be represented in this form, and all the intermediate values plus your input data are quantized integers, then you can convert them into their TFHE equivalent. And this graph represents the TFHE computation graph. So the linear operations are performed on integers, of course, and they are represented with sigma. For non-linear operations, they can be carried out using the table lookup. So just a reminder about the linear models. So linear models aims to establish a relationship between the input features and the desired output. So the prediction is simply a weighted sum of your input features to which you can apply, you can add a bias. And to get the inference, you just have to evaluate this formula. And here is the graphic representation in FHE, where sigma represents the linear operation between your x input, your x, which are your input, which is your input data. So here it's encrypted, and w, your weights. Is it encrypted or decrypted? Is it in clear or encrypted? In clear. No. So it's in clear because, as I said, for the moment we are only supporting the inference in TFHE. For the specific use case of logistic regression, you have to add at the end of your model a logic activation function, which involves to add and do this new box in your FHE graph. Regarding the decision trees now, they are more challenging than the linear models due to the nature of their structures. And the tree traversal using encrypted inputs are not possible in TFHE directly because the server doesn't know if he has to go right or to go left since the data are encrypted. But we can overcome this problem by evaluating all the decisions of the tree and transforming this tree to a tensor representation. There are many ways to do it, and in the machine learning team at Zama, we use the generic matrix multiplication algorithm to do it. And please note that the floating points in this graph are just for the sake of this example. Like I said, you have to use integers for TFHE. So in this graph, we have 5 leaf nodes and 4 decision nodes. And the observation has 5 features. So to transform this tree to a tensor representation, you will have to build 5 matrices. Matrix A, matrix B, matrix C, matrix D, and matrix E. The matrix A represents the relationship between your inputs data and the internal nodes in the graph. So basically, it's just a matter of reordering and assigning each xi to its corresponding internal node. The matrix B represents the threshold of the internal nodes. The matrix C for each pair leaf node internal decision node, it indicates if the leaf node is on the right or on the left or of this decision node. So if it's on the left, then it's +1. If it's on the right, no, on the left, it's +1. On the right, it's -1. And if there is no connection, then it's 0. For example, if we take the example for this value, 50, is 50 on the left of x3? Yes. So it's +1. If 50 is on the left of x2, no, then it's -1. If x3 is on the left of x1, no, there is no connection, so this will put 0. And if 50 is on the left of x4, no, it's on the right, so it's -1. For the matrix D, it counts the number of times that we went left from the root of the tree to the leaf. So, for example, for the value for t, we went 2 times on the left, so +1 +1, and 1 time on the right, +0, so we have 2. For the value 20, for example, we went 0 times on the left, so that's why it's 0. And finally, the matrix E, which represents the values of the leaf nodes. So we take your input answer, you multiply it by the matrix A, you will got 3.5, 2, 1.5, and 5. You will then compare it to the matrix B, which represent the thresholds of in your graph. You will get the input path. Your input path, you multiply it by the matrix C, small recall, that determines if now on the left or on the right, and then you compare it with the matrix D. So then you will get your output path, and you will have only one non-zero value in the output path. You multiply it by the matrix E, and you got your result. Is it clear?
Yeah, sorry. So when do you see whether the sign of the comparison is like greater or smaller in the matrix form?
Sorry.
Sorry, when you're doing comparisons, like if something is greater or smaller than 3, right? Like for every comparison that you do, the 3,
Yeah.
when you transform it into the matrix, how do you see if it's like greater or smaller than?
Okay. So here the example is for a floating point value of unclear data. So and this computation. Okay, so first you have to, as I said, compute your fast matrices, only just to flatten your tree, to transform it to its tensor representation. And then when, to figure out if this value is on the left or on the right, this step is handled in the compilation process, which is not good. And I will show you how in the next slide, I will show you how to represent a test comparison using a table lookup. I think that it will be. So now that we have built our 5 matrices, the tree can be represented with a series of 3 matrices. 3 generic matrix multiplication intervaled by 2 element-wise logical operations, and these operations can be represented in the TFHE graph. So for the matrix multiplications, it's linear operations represented by sigma, and for the test comparisons, we use the table lookup. So to come back to your question, to represent a test comparison in TFHE, let's say that the input is encoded using 3 bits, which means 8 possible values. So here the table lookup has a size of 8 values. For x3 greater than 3, which is in clear, so you know the threshold. So for the indexes that are less or equal than 3, it will be 0, 0, you put zeros. And for those who are greater than, you will put ones. For example, for the input x3 equals to 5, you will do table lookup of the index 5, which is 1, which means that you have to go to the left, to the right. For the demo. Okay, so for the demo, I will show you how to use ConcreteML library. And for each test, I will compare it with its TFHE with its scikit-learn counterpart. So here I generated 3 data sets, synthetic data sets. The first one has been generated using max classification and will be used for the linear model example. The second one, we will use it for the tree-based model, and the last one for the neural networks. So for the linear models, I've chosen a logistic regression. So first, you will split your data into a training and a testing set. You import your logistic regression in scikit-learn like you used to do. Here I just took standard, the default parameters. You fit, you predict, and then you evaluate the model and you display the decision boundary. Very simple and simple. In ConcreteML library, of course, the path will change. We have the same attribute as scikit-learn ones. And as I told you for built-in model, you will have an additional hyperparameter, which is the number of quantization bits. So you train your model. So at this stage, your model is in clear, the data are in clear, the training is in clear, and the additional the additional step in ConcreteML is that you will have to compile your model. During the compilation, it will automatically do for you the quantization. So in this case, we have a quantization post-training for most of the built-in models. This X-train is your calibration data set that I explained earlier for the post-training quantization. So it will help you to determine the quantization parameters. So you will know the range of the values that you will quantize your weights and activations. And from the crypto side, it will generate the TFHE graph that I showed in the previous slide. In our jargon, we call it a circuit. And it checks if the circuit is compliant with the TFHE requirements, which means that all the intermediate values are quantized and the maximum bit width in the circuit is less than 16 bits. 16 bits for the models that use table lookups, and we can go up to 25 bits for linear models. We generate the keys, private key and the evaluation key, bootstrapping key as well. We predict, and for the prediction, we can do three types of prediction. We can disable the TFHE parameter, which means that you will do your prediction on quantized data. You can execute the TFHE mode. So here you will perform the inference on encrypted data, or you can simulate the prediction. For the simulation mode, I will explain it for the neural networks. Then you evaluate your model and display the boundary. So as we can see, we have the same accuracy for linear models, and the inference time is 1 millisecond per sample, which is really fast. If we use, so we have the same accuracy as scikit-learn, and now if we try to decrease the number of quantization bits, the precision, you will see that the decision boundary has changed. And it will decrease the performance of your model. Regarding the tree-based models, so we do exactly like the linear models. We split the data. We take the XGBoost model from XGBoost, and we instantiate, train, and predict, then evaluate. So for tree-based models, it's slower because we use a lot of table lookups in the circuit. Do you have any questions? Yeah?
The quantization reduces the precision logically, and that's why it reduces the accuracy. Could it be possible to change the quantization formula in a way so that you get so that you don't get a linear quantization over the entire scale from minimum to maximum, but you increase the number of the points, the quantization between the middle point, and get less on the edges, so that because the problem are the points that are right next to the decision boundary. So if the quantization would be nonlinear, the points to which you quantize are nonlinear, would this be possible to improve this low bit, if reducing the bits for the quantization needed?
I think that we tried almost all the quantizations techniques, and we are still facing the same problem. So it doesn't improve the performance of the model. So here we see that to perform one simple, we are about 1 minute, which is quite slow. But we have almost the same accuracy as the scikit-learn accuracy. So same problem. If you change the precision, you will have a different boundary, and it will decrease the accuracy of the performance of your model.
So how much is the difference between the normal scikit-learn library and the in terms of time, in terms of space?
Okay, so in terms of accuracy for linear model, we are quite the same, even for the inference timing, because we don't use table lookups. So the computational power is less than the tree-based models. For tree-based models, since we use a lot of table lookups, so it will increase the size of the circuit, to increase the size of the circuit, and the inference timing will increase as well. So in terms of the timing, I would say that definitely it will be slower, for sure. But for the performance, you can reach the accuracy of the scikit-learn if you tweak your model. So here I didn't tweak the model, I didn't change the default parameters, but if you do it, you are able to reach the performance of scikit-learn.
So if I'm getting the same accuracy like the second one, and even if performance wise storage abilities are slower, so why I would use the box?
To protect the privacy of your input data. So you will have a trade-off when you use not only TFHE, but almost all the schemes of FHE. You will expect to have it, to have a latency. So it's a cost to pay. So you either choose to maintain a good accuracy and have a slower inference timing, or you will say, okay, I will decrease the performance and I will have a faster inference timing. And it will, of course, depend on your use case.
Actually, my main concern is like, actually, I was thinking that the scikit-learn that you have mentioned is using some other FHE family, like FHE scheme like CKK. So I was thinking that you are using their scheme for the same.
No, it's for. You mean for the complete executes or for the scikit-learn
For
executes?
anyone, get with scikit-learn that is getting 97%.
Yeah. Yes.
So it will be a fair comparison if you use, for example, the CKK sorted and then you are comparing it for the scikit-learn.
Yeah.
Both of them will be
I think that we have some comparisons for that, but I don't have them. But if you want, I can send them. Okay, so now regarding the deep neural networks. So it's possible to do deep learning in TFHE. The nature of the structure of neural networks fits perfectly the FHE graph operation. But for custom models, there is some work to be done from the developer. So you have to manually quantize your model. The best practice to do it is to use quantization over training and to take an already fine-tuned model to do it. Usually only few epochs are enough to catch up with the floating point accuracy, and you can easily do it with the help of Brevitas. In concrete ML library, you also, like I told you before, you can have 3 modes of inference. You can disable at all FHE, or you can use the real FHE executions, or simulate the homomorphic operations of FHE. What does it mean? It means that with this simulation mode, you will mimic the behavior of the homomorphic operations without actually performing the real FHE operations. During the development phase, it's really useful because it saves you a lot of time. And this simulation mode also reproduces the payroll probability that I shown in the first slides, which is caused by the noise in the ciphertext. Usually, the accuracy of a simulated mode is like the one of the real FHE execution mode. And if you are not happy with your performance, because the quantization, as we saw, reduces the performance of your models, you can use some advanced techniques like pruning, which means removing some neurons to reduce the complexity of your model, or play with some crypto parameters like adjusting the error probability of your TMU, or enable another type of bootstrapping. So at the moment, we have what we call a rounded bootstrapping, programmable bootstrapping. So you can play with these advanced features in CompleteML. And once you are happy with your performance, you can execute the real FHE execution on your encrypted data. And you can also deploy it using the client-server API that we provide in CompleteML. Almost all layers are supported in CompleteML, which gives you the flexibility to build any model you wish. But it's highly recommended to keep the size of the accumulators as low as possible. And currently, CompleteML allows up to 16 bits of precision for a reasonable and fast execution. Otherwise, okay, so like I told you, you have as a developer to quantize manually your network. So for example, if I take this network and I would like to convert to use quantization aware training, we can use the Brevitas library to do it. Brevitas library is a PyTorch library for neural networks for quantization, and it supports quantization aware training. Almost all Torch models have their equivalent in the Brevitas library. For example, the conv2d becomes quant-conv2d, ReLU becomes quant-ReLU, and so on. And of course, you will have some additional hyperparameters to take care about. You will have the weight bit, the weight bit width parameter for the linear operations, and you have also the quantization protocol, which we call weight quant. So here you can see the documentation of the Brevitas library, but from my experience, you can just take the default parameter and it gives you a good performance, good results. The new thing that you will also have to take care about is to quantize your input. In the printing models, this step is also handled under the hood, but once you would like to convert custom models to FHE, you have also to think about it. So to quantize your input is really simple. You just have to add a layer at the top of your model using a quant identity layer. And like this, your inputs data are quantized. Okay, so let's see in practice how it looks like. Okay, so like other examples, we split the data. If I'm using torch, so I have to convert the data to a tensors. Here I imported my model. So it's a really simple model. I have just two hidden layers. And here is the conversion of this model using Brevitas library. So really simple. I have the so here are the parameters of the model. and you can train your model. Okay. Okay, you can train your model. So here, this is the training in floating point. So you have an accuracy of 81% for your test set. Now for the quantization aware training, if you recall the diagram that I showed before, you will have the first step is to quantize brutally your model, your network. So you will see that you have a big loss in the accuracy, but you can retrain your model and it will increase your accuracy. So here, of course, I just took few epochs. I didn't put a lot of efforts to reach the floating point baseline, but it's possible, and I will show you this with the built-in models. So like we did for built-in models, you have to compile the model. So here you have to use another function for the compilation, because here I'm using Brevitas and quantization aware training method. And you have a set of quantization of compilation functions depending on how you would like which model you have taken, if it's Keras or TensorFlow, if it's post-training quantization or quantization aware training. And we check the maximum bit width of the circuit. So like I said, it's really recommended to have it less than 16 bits. And then we do the inference in TFHE. So as we see, it's 60 seconds for one sample. Okay, and if we to plot the performance of our neural network, we see that the decision boundary is not that good, with only 3 bits, which means 6 bits in the circuit. The performance, the decision boundary doesn't look really good. But if we increase the number of bits to 4, so here we can see that we have a training, an accuracy on the training with 90%, which is quite good. But the size, the maximum bit width of our circuit increased to 8 bits, and it's almost 7 minutes to perform one inference. If we use the built-in models, so it's like a multi-layer perceptron for the scikit-learn. So here we have 90%, and with the concrete ML counterpart, yeah, we have almost 90%. So it's possible to reach the performance of the floating point, but there is a price. There is a price. In concrete ML, we have 20 very well detailed tutorials for those who would like to get started with concrete ML library. We also, 2 quarters ago, we have tackled some well-known use cases for the classification task in computer vision for MNIST and ciphertext datasets. I will show you the performances in the next slide. We have 2 well-known detailed tutorials where we show how to train from scratch a quantized model, and another one how to just fine-tune, like I showed you in the demonstration, just to fine-tune a model. And we show how to convert a VGG 11 to its FHE equivalent. We also have some use cases taken from Kaggle, the Titanic and the credit scoring, well-known use cases. Like I showed you before, we have 3 use cases available in FHE space that I invite you to try out. We have the sentiment analysis, the healthcare prediction, and the image filtering. And for this quarter, we are trying to convert a large language model to its FHE equivalent. So it's a big task. So to begin with, we just started by converting just small pieces of the LLM model in FHE and performing the inference encrypted for this piece. And we have also other tutorials in concrete ML. For the performances, like you can see, we are not really far. Oh, excuse me.
Can we also use this concrete ML on transformers? For example, for images, I see that there are 3 types of data sets, but the most popular one is images.
Yeah.
Is it not too big to not too long to take results, because you tell that you have to wait 7 minutes to evaluate, and MNIST is like very small image, and ImageNet is really big.
Very big, yeah, very big. So it's possible to use the ImageNet data set, but it's really slow. It's really slow. And we have the computation power to do it, but for standard users on their standard machines, it's not possible. So that's why we didn't showcase the ImageNet filtering. The ImageNet data set. The thing that I will say, I was about to say is that for 2024, we are expecting some improvements on the hardware part. So with these improvements, we wish that the inference timing will decrease, and we will make it available for our users, at least to let them try.
Attention modules, or because you showed convolutional layers, and can we use this concrete ML on attention models?
Yeah, of course. We did it with the linear models, with the with the LLM models, but at this stage, we are not able to quantize all the to convert all the model to its FHE equivalent. So we just started with this task, and for the moment, we are just inputting small pieces, and then we'll see how to do the entire attention heads.
Thank you.
Keyboard. So, like I said, we are not really far from the state of the art, but for custom models, some works needs to be done some works is still required from an inference timing point of view, and also the automation of the process of conversion to a custom model to its FHE equivalent. To conclude with TFHE, it's a promising technology to safeguard the privacy of the users, like CKKS. It's also another scheme that is willing to do that. Concrete ML is user-friendly, and it's compatible with many other libraries like PyTorch, Scikit-learn, and Keras. Any scikit-learn pipeline is possible to use with concrete ML models like grid search. We can use also grid search on our concrete models. For tree-based models and linear models, they are accurate in TFHE, tree-based model are a little bit slower, but as I said, there is a trade-off that you have to choose. For custom model, there are more constraints, and as you saw, you have to manually perform the quantization and check if the circuit is compatible or not with TFHE. And for the moment, TFHE is still slow. We are only, for the moment, we are only supporting CPU, but at the end of the year, we are expecting some improvement from the hardware path. We are collaborating with some hardware companies. We also have a hardware team that is working on the acceleration of the FPGA. And finally, no crypto knowledge is required to use computer library. So just have be a data scientist and to use some tricks to maintain a good accuracy while maintaining a reasonable latency. Some useful links that we would like to share with you. We have our GitHub repository. Here is our GitHub repository. You are very welcome to contribute to ConcreteML since everything is open source. You can submit pull requests or write issues. We are really responsive. And we also have well-known documentation about our work. We have two channels to reach out to us. We have the Zama community for ConcreteML for the machine learning team, and also the Discord chat where you will find all the teams of Zama, including the cryptographer, the compiler team, optimization team, and the hardware team. We are very, very responsive, so you can ask all your questions there. And finally, we have a Booty program where you can take on challenges and get rewarded. So thank you for attending to this presentation. And here are my contact details, so feel free to reach out to me if you have any questions regarding what you are doing at Zama or regarding the presentation. Thank you.
Yes. Are there any questions, Celia? Yes, we have a question over there.
Yeah, you have mentioned that concrete.
Yep.
You have mentioned that ConcreteML supports the pipelines from scikit-learn. Does it support some custom data transformations, for example, one-hot encoding of the certain column, or even some transformations written by the users? Because scikit-learn basically supports making a custom transformation from a function written by a user in Python.
I'm not sure that I get your question. It means that before training, you would like to apply some transformation on your data?
As a data scientist, I regularly
use Scalar standard DB transformation.
for that normalization, one-hot encoding.
Yeah, you can do. Okay, so since the FHE is only applied in the inference phase, so you can do whatever you want before this phase.
Yeah, but in scikit-learn, I can build a pipeline with the transformation.
You mean with the pipeline?
Yeah,
you can do it.
And it will transparently work in ConcreteML during the inference.
Yeah, for the inference, I haven't tried it. I know that during for your training phase, so that will be for sure applied. I haven't tried on the encrypt. So what you can do is apply locally the transformations and then encrypt the data.
Yeah.
But in the pipeline,
Yeah.
in the pipeline, I haven't tried it. I will do it and I will come back to you.
Okay, great, thanks.
Thank you, Celia. Great presentation. I really enjoyed watching it. I just have one question on the maximum precision. So you mentioned that the current precision is 16 bits. I understand it's going down to the HE library. Are there plans to extend the precision to something larger, or maybe even add floating point support? Just wondering.
For the moment, I know that in the TFHE library, they are working on floating point. But for the moment, it's not yet delivered, and we are still not using it in the computer library. But I think that for the moment, we are not planning to extend it to more bits, because even with this precision, the latency is quite slow. So we are more trying now to work on the hardware part. And some optimizations on the crypto side.
So,
Yeah.